So in this lecture, we specify what we want from an encryption scheme as far as security is concerned. So the gold standard is perfect secrecy, and informally what it means is the ciphertext reveals no information about the plaintext. Now, how do we formalize this from a mathematical standpoint? Well, what we want is that given two messages in one ciphertext, the likelihood that that ciphertext encrypts those two messages is the same, which means that that given ciphertext gives you no information about what possible plaintext it could come from. Okay, so here's the mathematical formula that gives formalizes this definition. You want that the probability when all the keys are distributed uniformly at random, so that is what we mean by that symbol. The key K is chosen uniformly at random in the key space capital K. The probability over all those possible keys that the encryption of M0 under that key VC is the same as the probability where, again, under a choice of a key uniform at random in the key space, the encryption of M1 be that same ciphertext, meaning a given ciphertext is just as likely to be the encryption of any other message in the message space. Okay? So first of all, let's take one of these examples from the previous lecture, which is Caesar cipher. So does the Caesar cipher have perfect secrecy? Well, obviously no, because we saw it was so insecure. What are the chances it has what we just described as the gold standard of security, right? But let's use the mathematical formula that we just gave. So let's take that particular choice of C, M0, and M1, okay? And let's calculate the corresponding probability. So how many keys could potentially satisfy the encryption of M0 under that key is equal to C? Well, let's see. M0 is BBB. To encrypt M0 into C, there's only one possible key, which is a shift of, well, in that case, I suppose a shift of 25, okay, or minus 1. So exactly 1, which is K equals 25, okay? And now how many Ks satisfy the encryption of M1 is equal to C? Well, it would have to be that there's a shift of 0 to go from A to A, but then that same shift of 0 could never map B to A. So the answer is 0. It's just impossible to have the encryption of M1 be C. So when you make a choice of K uniform at random, the probability of having encryption of M0 equals C is 1 over 26, okay? Because K equals 25 is the one and only shift that satisfies this property, while the probability that the encryption of M1 be C is just 0, and those two values are different, and because they're different, they do not satisfy the condition for perfect secrecy, and the C cipher is not perfectly secret. Okay. Now there is one very standard example of a cipher that has perfect secrecy. It's called one-time pad or the Vernam cipher. So in this case, plaintexts are strings of bits. Okay, here I'll say that the length is n, and the key is a string of bits of the same length. And the encryption process is the following. You take your first bit, you XOR it with the first bit of the key, and you get the first bit of your ciphertext. And then you repeat that with the second bit of the message, second bit of the key, in which gives you the second bit of your ciphertext, and you do that until you get the nth bit. And here I want to recall that the XOR operation is defined here, and it's basically an addition mod 2, so 0 XOR 0 is 0, 1 XOR 0 is 1, the same as 0 XOR 1 and 1. The only difference basically between a simple addition is 1 XOR 1 is 0. Okay, and that policy is actually what allows you to decrypt. So how do you decrypt? Well, you use the fact that whenever you will XOR a bit of the ciphertext with a bit of the key, you have by commutativity, you have this thing that you know for sure is 0, because 0 XOR 0 is 0, and 1 XOR 1 is also 0. Okay, so whatever k is, you know that whenever you XOR it by itself, it's always 0, which means that you take the ciphertext, the bit I of the ciphertext, XOR with the bit I of the key, and you always get the bit I of the message. So this is how you would do it, and so on and so forth, until you get all the messages, all the bits of the message. So let's just work out an example. So what is the key, the encryption of that message with the key k equals given by this bit string? Well, here's the answer, and I will let you work out all the details. Let's just see what happens on the first bit. So 1 XOR 1 equals 0, which corresponds to the definition of XOR, and you can do that for all the remaining 20 bits. Now, what about the perfect secrecy? Well, one-time pad has perfect secrecy. For example, we can show that whenever you have a message, so let's say M is a 5-bit message and C is 00111, there is one and only one key that satisfies encryption of M under the key K equals C. In that case, it has to be 10110. That's the one and only. So for each M and C, there is a key, and that key is uniquely determined by M and C. And in fact, the way you uniquely determine it is that if you say, if encryption of M under K is C, that is the same as saying that K is C XOR M. So there is a key and it's uniquely determined. Therefore, if you make a choice of key uniform at random, the probability that the encryption of M0 be C is 1 over the cardinality of the key space. And therefore you do have this property which defines the perfect secrecy. Okay, so in that particular for that particular cipher, we do have perfect secrecy. Now, perfect secrecy doesn't mean that we've achieved sort of a perfect cipher that we should be using all the time and not care anymore about improving it. The reason, in the case of the one-time pad, we have some notable disadvantages. So first of all, the messages are not authenticated. What it means is if somebody tampers with the encryption, then they can produce the encryption, a perfectly valid encryption of a totally different message. So for example, if Alice sends that message to Bob, then Eve can intercept the message and XOR that ciphertext by, for example, this thing. And then instead of getting an encryption of the right message, Bob can decrypt and receive a message that is exactly the XOR of the original message by that amount here. So it lacks authentication. The keys also are as long as the message, which is extremely inconvenient in the case of long messages, and that is a big problem. And in fact, although it is a big problem as far as perfect secrecy is concerned, it is actually the best you can hope for, because there is a theorem due to Shannon that tells you that for a cipher to have perfect secrecy, necessarily you have to have that the key space is larger than the message space. Now, to relax this condition, there is a way to mimic the behavior of the one-time pad, but by using smaller keys. So we call those ciphers stream ciphers, and the way they proceed is by using an intermediate module called the pseudo-random generator. And the goal of the pseudo-random generator is to take a key which is presumably small, so for example of size S, and then and then create a long string of random looking bits of length n, where n is going to be the length of the message. And the way you would encrypt is exactly the same way as the one-time pad, except that first the key goes to the pseudorandom generator, and it produces g of k, which we define to be the key stream, and that gets XORed bit by bit to the side, to the plain text, and that creates the ciphertext. And then the decryption works exactly the same. You recreate the key stream with your key, and then the key stream gets XORed bit by ciphertext to give you back the plain text. Okay, so it all boils down to whether or not your pseudorandom generator actually looks random. So this is the encryption process. As I said, you create the key stream and then you XOR it bit by bit to this plain. Now we can work out an example for if you have s equals 5 and n equals 10, then this is the most simple way you can think. You can create a pseudo-randomness by, for example, repeating your key. Of course, repeating your key doesn't really look random, but is, I would say, the most obvious thing you would want to do if you had a small key and you had to encrypt a long message. So I'll let you work out the image of that message key by, so we can see that the image of that key by G is just going to be the repetition of, and so on and so forth. And then you want to encrypt the message M. Well, you XOR bit by bit. So you take 1 and 1 and you XOR, you get 0, then you get 0 and 0. I give you 0, then you get a 1 XOR to 1, that's a 1, 0 XOR to 1, that's a 1, and so on and so forth. Okay? So now let's move on to the definition of the security of pseudorandom generator. So remember, what we want is for a pseudorandom generator to look random. So there are going to be two ways to characterize the security, and these ways are equivalent. So the first thing is more of a necessary condition, and we'll show that it's actually sufficient. We'll mention that it's actually sufficient. And it is the fact that if I give you I bits of the key stream, you cannot be able to guess the I plus 1th bit with a probability significantly larger than 1/2, which is a coin toss. Okay, so we call that predictability. If a pseudorandom generator fails this, it means that it's predictable. So we say that your random generator is predictable if there is an algorithm that will given, and so the algorithm is denoted by A, and that is the probability, with the probability that A that takes as input the bits 1 to I of G of K guesses the bit I plus 1 of G of K with probability 1/2 plus something, where the something is non-negligible. Okay? So here the notation, this means the bits number 1 to I of G of K, which itself is a string of length n, and this is the bit I plus 1. Okay, and what do we mean by negligible? Anything larger than 1 or 2 to 30. In this class, of course, we'll have very simple cases. So for example, we'll have negligible will mean usually non-negligible will mean 1/10, 1/2, 1/4, those sorts of values. We'll never have very, very small values. Now, why do we define that advantage as this is the advantage? So we say that the probability has to be minus 1/2. Okay. And let's give an example. So that's the advantage, and a small advantage would be something around 0, and a large advantage would be something around 1/2. Now assume that you have this property here that is satisfied. That will mean that gx of I plus 1 will be always gx of 1 XOR gx of 2 XOR until gx of I, which means that you have a deterministic function for gi plus 1 with respect to the ith values of g to the g of x. So the advantage here is that for an adversary that returns exactly this, then the advantage, well, will be that defined by the fact that the probability for a choice of k that my adversary returns the right bit is exactly 1. Okay, so we have g of k for 1I, that equals g of k I plus 1 with probably 1. And then the definition of the advantage is that you take that probability, you minus 1/2. So the advantage is 1/2, which is the best advantage you can hope for. Now, that was to define what it meant to be unpredictable. But what does it actually mean to look random? Okay, so we need that any efficient algorithm looking at a string of length n behave the same when looking at a g of k where k is chosen at random, or looking directly at a random string in 0, 1 to the n. So here's what we want. We want that these two probabilities be equal. And so that's how we're going to define the advantage. The advantage is going to be the absolute value of the difference between adversary looking at g of k for a random choice of k returns 1 minus the probability that the adversary looking at r for a random choice of r returns 1. If that is small, then you have a bad advantage. If that is close to 1, that means that your adversary, your algorithm, behaves very differently when looking at g of k versus looking at random strings. And that means that the string doesn't really look random. So for example, let's assume that there is, say, the nth bit that satisfies that the probability that gk sub n equals 1 is in fact 2/3. Well, we can define an adversary that returns 1 if and only if x sub n equals 1. So what would be the advantage of that? Well, you know that the probability over choice of k at random that the adversary returns 1 will be 2/3. But on the other hand, the probability for a random choice of r that the same adversary returns 1 is only going to be 1/2. So the advantage here, by definition of the advantage, is the difference between those two values, which is 2/3 minus 1/2, which is going to be 1/6. Okay? So, security and unpredictability. It turns out that a secure pseudorandom generator has to be unpredictable. And that's not really hard to see, because if something is predictable, you can show that it has to be insecure, which makes sense, but it's something you still need to prove. So for example, you can show that if you have an adversary that predicts efficiently the bit number I plus 1 from the bits 1 to I for some I, then you can define an algorithm that looks at the entire sequence, applies that previous adversary to the subsequence 1 to I, and returns 1 if that first adversary guesses successfully. and otherwise return 0. And the advantage of that adversary is essentially linked to the how much above 1/2 is that probability here. Okay, so it means that if A is efficient, then so is A prime. Okay, so it turns out that also being unpredictable implies being secure, and that's much less obvious. So, but that shows in the end that unpredictability and security are the same. Okay, or being insecure and being predictable are exactly the same. So these two notions are in fact equivalent. Now, last but not least, we're going to introduce the notion of semantic security under a one-time key. Okay, and this will be what we want as far as the security of the cipher is concerned. Previously, we were defining the security of a pseudorandom generator, but now we're going to define what we want of a cipher, in particular of a stream cipher, but in general of any encryption scheme. How do we want it to behave as far as security is concerned? We saw at the very beginning that perfect secrecy was going to be a little bit hard to achieve unless we agree to have the size of keys being at least as long as the size of messages. We can achieve what we call semantic security with much smaller keys. Okay, so here's the definition of semantic security. We want that any adversary who makes a choice of two messages of equal length and sends it to a challenger who chooses a key at random and sends back the encryption of one of two messages, we want that adversary receiving one encryption to be unable to decide with good probability which message was encrypted. To formalize this, we define two experiments. In the experiment 0, the adversary is in front of a box that returns encryptions of M0 with a random key. So you have your adversary. Your adversary chooses two messages with same length, and while at the same time the challenger chooses a key uniformly at random. The adversary sends those messages, and the challenger sends back the key. The adversary then returns 0, 1. That's for experiment 0. In the other experiment, the adversary is in front of a box, and this time the challenger returns always an encryption of M1. So the adversary always behaves the same, chooses two messages with same length, while the challenger chooses a key at random. The adversary sends the messages. The challenger encrypts always M1 and sends it back to the adversary, who returns 0, 1. And here what we're trying to measure is how differently the adversary behaves in those two experiments. If the adversary behaves the same in the sense of the output, 0, 1, then it means that it's really hard to distinguish whether or not which encryption is the encryption of M0. On the other hand, if the adversary is capable of behaving very differently, experiment 0, experiment 1, then it means that there is something about the encryption of M0 and M1 that gives away which message was, which is bad for security. So here's how we define the advantage. So we define first an event W0, which defined by the adversary returns 0 in experiment 0, while W1 means that the adversary returns 0 this time in experiment 1. And the advantage is defined as the difference between those two values. Advantage of 0 means it's secure. It means the adversary is not efficient, while an advantage of 1 means that it's insecure. Okay?